my talk is going to be an introductory talk of the transformer architecture, which is the foundation of the current AI system. So I would like to start with the question of what AI actually is, and I want to give you my personal view and my personal kind of definition. I want to start with these two pictures. Do you remember this? It's Google Glass, yeah. And one of the first version of Google's self-driving cars. So these pictures are from 2012, actually. And they're an example of Google trying to integrate technology into our world, into our lives. And Google Glass failed prominently. And the self-driving car is coming soon, I'm really confident. But it took them many years, right? So yeah, when they started, they were thinking, okay, we do some object detection and then we define some rules, like we know how traffic works, and then we'll convince the car to drive itself. But it wasn't that easy, so they found out the hard way. It was difficult to, connect the IT system with the human world, and that's what I want to base my definition of AI on. Is AI, in my opinion, is a system that has access to a world model of human level complexity, like the car, the traffic around and so on and so forth. And within this framework, it can understand its situation and derive results and actions. And the system is capable as a human usually. Skillful, so not intelligent, but capable. And it can actually close the gap, right, between our world and the computer world. I really want to go a bit back in time to the 1950s, actually, where this whole journey started. So I'm going to take you on a journey from 70 years ago until today and show you what happened. So this is showing Frank Rosenblatt with the Mark I perceptron. So this was like the first approach to create a machine that was able to learn, to mimic like what they were thinking at the time, how the human brain works. And they were, that was a time before computer chips were invented, so they were actually cabling stuff and had a reception and then hopefully some output, but they were also tuning it manually. But the key ideas they had were really valuable, and I'm going to show you an example with data applying this perceptron that they introduced at the time. So let me show you the data. This is a data set that has some metrics of wines, of Portuguese wines in it. So we have some values that were measured at the certification process, and then you have a label like a taste preference from humans. So they can either be good or bad. So I want to implement this perceptron based on this data set. And if we now write it out, I'm not using wires here, but obviously a computer program in Python. And if you spell out the formula, you end up with such a simple formula, right? So you have the inputs, which is in this case alcohol, sulfur dioxide, and you just multiply them by weights, W1, 2, and 3. Add that all up, and if the sum is bigger than a certain value B, it can be considered a good wine and otherwise a bad wine. And that's all that is, behind this perceptron. Weights and biases are the terms for these, and they're usually considered the model parameters because it's a model, right? Input, output, and then some variables that define how the model works and acts. Okay, so you apply this formula, you multiply, add, and see if it's like bigger or smaller than a certain value. What you can see here for a single example, we have some values, put them in. Okay, it's very small, but it's like small numbers. You multiply this, add it up, and the result is 0.43. And if we take 0.5 as the limit, right, this would be a bad wine. And then you can go and define this for each wine. And the next time you are in the certification process of a wine, you can immediately tell if the wine is good or bad. Well, kind of, because the prediction is not very good. But nonetheless, now we have introduced this so-called perceptron. This is what we saw earlier of Frank Rosenblatt, but in today's version, right? It's a software abstraction. And usually you see it depicted like this. You have your inputs, the weights, and then you sum it up, and you define some threshold, B, and an activation function to tell whether it's good or bad. And at the time, they just used the step function, so it was either 0 or 1. And today we use something more smooth because mathematicians don't like edges in their functions. It's hard to derive. So this is a sigmoid or something like this. So. But other than that, it's the same structure. And still, although the idea is quite old, it's the building block of all neural networks and modern AI applications. So what we did is we built a binary classifier so we could tell whether the wine is good or bad. And it's actually the implementation of the first learning machine that someone came up with. And yeah, like I said, the perceptrons, that's what they called it at the time. Today we also say neurons, are the building blocks of modern AI. And I want to show you how to do the next step now. So same data set, still some wine parameters, but we want to do a bit better now, not just differentiate between good and bad wine, but we actually have a rating. Now can we predict the exact rating? And we can do this by just stacking up the perceptrons. Yeah? This is what a neural network looks like. And we define one output, one perceptron, so to say, for each class in the possible outcomes. So quite obvious. So yeah, for each class you have 3 weights now in this model. And before I show you the result, I want to discuss one thing quickly. Since at the time, and they were tuning the parameter of the models manually, just by trial and error. Of course, this is not what we do today. It wouldn't be feasible if you have like a lot of parameters. And the parameters of the model, which describe the behavior and the outcome, are now determined by a technique called backpropagation. And this makes use of a so-called error function, which is just considering the difference between what the model puts out and what we want to have, right? So y would be the result of the model, the current result with the current weights and biases. And d is what we have in the data. So we compare if they're different, it adds up. If they are correct, they're the same, they don't add. So the error function gets big when we are wrong, right? And the error function depends on the weights. And so we're going to minimize this, and this we're doing by getting the derivative down to 0. This is a mathematical term, but think of like trying to calculate the change rate of the weights, and then by moving the weights depending on how big the change rate is. So that's the idea, and that's an iterative process. You calculate this error for each sample, for each class, and then you go through your whole list. Add it all up, you get the error, change the weights accordingly, so the error gets smaller, and then you do this several times and end up with a good result, and that's backpropagation. And this would be the result for a wine sample, for a single wine. And now you can see here, the 4 is indicating that this is probably a wine rated as 4 or 5. So in that sense, we have 9 outputs. If I display it like this, we have like a distribution. So it's a neural network applied and appearing as like a statistical model. Okay, so the output is a distribution. That's a concept that I wanted to introduce here. We have stacked neutrons, stacked perceptrons, a statistical model, and this is the output. Okay, so the key takeaways of this section, I introduced neural networks as a combination of neurons or perceptrons. We can apply it as a statistical model. And I've quickly talked about this way of finding the right parameters of the model, which we call backpropagation. And this is because in this talk I'm going to put some medals out for very good ideas in AI, and this would be my first medal. So this backpropagation, that was really a good idea. Okay, let's do a step further. We had this neural network, and I'm going to show you a slightly more interesting, but also slightly more difficult example. The handwritten digits is a very classical data set. So handwritten digits and put into a grid of 14 by 14 pixels, and each pixel has a grayscale value, right? So that's our input. And of course, the task will be to find out what the digit is. So, but the data itself, when it goes into the model, looks like this: just a colon of numbers, and the small values indicate the white pixels, and the bigger ones the black. Okay, and so what's that?
Oh, okay, three dimensions: intensity, horizontal, vertical. No, why then that was 3-dimensional?
No, it was just a list. It was just a list. Oh yeah, you have the 3 brackets. I don't know. I just wanted to display the whole list. Each pixel corresponds to one number. That's my message here.
I got it. From what I understand, it's basically it's not 3-dimensional. It's basically a group of b-dimensionals.
Maybe it's just a batch.
That is just one number. That is just one 14 by 14, but it represents the lines and the columns, and then it has the possibility to add several others images. That's just one image.
Okay, anyways, I'm not sure in what state this variable was when I printed it, but I wanted to show just the list of numbers, okay? The way you format it, it's not relevant yet, no? And, right, so before we had stacked perceptrons, and now not only can we stack them, we can also chain multiple layers together, and this is the architecture which is applied here, right? I left out the inputs, which would be here, but it's too much to display because it's 196 input neurons, so to say, but just imagine they would all be here. So this would be the first active layer. And yeah, the first learning is actually, although it's quite a simple structure, it's very powerful. Yeah? It has very good determination power of these handwritten digits. It's almost like seeing all of the digits correctly. So that's the first point. And the second one I want to emphasize here, I have 3 examples of 9s and the corresponding activations here, right? So one is very high activation. So inputs are high that end up in this neuron. So the first 2, they're very similar, which doesn't surprise us because the first 2 digits, they look similar. If you put in the same data, you get the same results, right?
Sorry, just a question. So the inputs could be here, the edges, the colors, or the gradient of the color, for example, right?
No, the input is really just
But could be, right?
the gray. In this case, it's really the gray value of each pixel of this handwritten digit. Okay, and it's split into 14 by 14 grid. So just a few pixels, not very many. 14 by 14 is 196. So for each pixel, one value, and that goes into the neural network. And what you see here is the activation. So you remember input, and then the perceptron was just a sum of the products. And if the sum reaches a certain value, then it's saturated at 1, depending on your activation function. So this one is fully activated, the yellow one, and the others as well. And you see patterns, right? And that's what I wanted to show here. So the first ones are very similar, and the third one is different, right? Because the stroke is showing into a different direction, and we see some similarity, but also some difference. So what we learn here is that in this process, of feeding the data through a neural network, we learn abstractions, right? Concepts, as in like a little circle here, a line here, something like that, right? Just to give an intuition. And depending on if we find these patterns, certain neurons are activated and certain others are not. So let's go to the second one. Now looking at the third example, and you see in the second layer, the activations are pretty much the same, right? So although the input looked quite different, already in the second layer, in the second iteration, so to say, the second order of abstraction, the neural networks finds the same patterns, right? So although this line points into a different direction, and of course in the third one they're all saying, okay, this is definitely a 9. So from layer to layer we abstract more, we find like broader patterns, and we lose information, and we keep just the information that we need. In this case, what the neural network is supposed to do, right? So to find just the digit that is represented by this number. And so this is a very good learning. This is also something that I wanted to stress. I was playing around with different shapes and so on, trying to put together different shapes, and I found that this was actually clearly indicating this is a 4. This is a 4. So the network thought this would be a 4. And it tells me, look, the network decided if I find a pattern like this edge here, this is a 4, right? So the network determines what the shapes, the concepts are that it wants to focus on in order to fulfill the task, right? And it's not always what we would expect, but it's what it needs to do to get the job done, right? So everything we learned in this section, I want to summarize by words of Geoffrey Hinton. I don't know if you've heard of him, from a paper from 1986, and he says, we describe a new learning procedure in this paper, backpropagation, we've seen that, for networks of neuron-like units. The procedure repeatedly adjusts the weights of the connections in the network so as to minimize a measure of the difference between the actual output vector and the desired output vector, right? What we've seen. So, and as a result of the weight adjustments, internal hidden units, which are not part of the input or output, come to represent important features of the task domain. And the regularities in the task are captured by the interactions of these units. So this features aspects, that's very important. One of the most important ideas, I would say. So he was quite a visionary. This is from '86, and he described everything that we've just learned in the slides, and which is so relevant in current AI models. And this is why he was awarded the Nobel Prize last year, Geoffrey Hinton. And I would say he was the one who was like persisting on this idea of the hidden states and representations of the concepts and the attribution to these concepts, right? And yeah, therefore he received the prize. So the takeaway of this section: the machine abstracts concepts and creates representations, right? It condenses relevant information and removes noise. And now the inputs and the internal states can be seen as attributions to the aspects of the representation that you find in the next layer, right? From one layer to the other. So this is something that, I would like you to keep in mind, that from now on, when we look at like deep neural networks inside the network, we're only working with representation. It's always representations. It's always concepts, and the weights indicate to what extent the step before attends to these concepts. Okay, and this is something that I would also like to reward a good idea medal to. So we're leaving the visual space, the handwritten digits, and are now coming to words. We're going to the year 2012. When bright people had the idea of doing something similar with words. right, to find representations for words that incorporate these concepts and the attributions to the concepts as well. And the way it was done was they took a big text corpus, assigned an index to each word, right? And then they took single words, like consultant here, and compared that to the context. So in this case, 3 words behind and after the words. And we're comparing the words to the context. And the idea is that the word has something to do with the context and is somehow related or similar to the context, right? And in that sense, they were trying to extract these representations by using neural networks, of course. And the structure of the neural network they were using at the time looks like this, like a sparse autoencoder. On the left-hand side, you see the index of words. In this text corpus, you have 3 million words listed. And yeah, so when we get back to this example, you would just assign a 1 to these words that are in the context, advice from A for our strategy. I've indicated this here. And with these 1s, these weights are being active, and I have the opportunity to build a representation of what they mean. And this representation is then supposed to predict the missing word, in this case, consultant. And 1 would be the desired output. Usually there's not a 1, but some value close to 1, and the others probably also have a contribution, but that's the idea. And so, yeah, in the middle you have the feature space. So in this case, 300 nodes, every node somehow representing a different concept reflected by these words, what they describe, right? So in that sense, it's concepts from our world, since usually text describes what's around us. And yeah, the weights are the attributions to these concepts, also known as the embedding. Now that's the terminology that you usually hear, the embedding. This is an embedding. Okay, so you train that data in the same sense with the backpropagation which we discussed earlier, and you would end up with a bunch of numbers, like 300 numbers for a word like consultant, right? So these are then, the attributions to the concepts again, or what we call a word vector. And just, to make it a bit more tangible, like when you think about what can that be, like for consultants, think, okay, maybe this indicates analytical skills, this is business association, whatnot. Nobody knows because these features are latent, so we don't know what they mean, but for sure they have some meaning. So we don't know, but we can do something with it, right? So for example, we can find similar words to consultant with quite good results. And we can also do some a simple way of communication between words, right? So here's indicated what's similar to Paris, Parisian, so places in Paris. But what happens when you subtract the word vector of France and add the word vector of Italy to Paris? And then surprisingly, or not surprisingly, but yeah, you would see Italian cities as most similar to this expression. So that means, by adding and subtracting, you're communicating in this embedding space. And that's a great achievement. And I do remember that at the time I was pretty excited when I read about this, when the paper first came out. It was somehow, connecting the machines to, like, our world. Third example, yeah, you can try to find a representation for a whole sentence or a phrase. So I was using this one, getting out the nouns, averaging these vectors, and I was looking up what's most similar to, like, the representation of this whole sentence, and surprisingly found very good similar words, like the Portuguese word for football, right? Although this approach is really very simple, but it's working quite surprisingly well. So these are word embeddings. Key takeaways of this section. With these word embeddings, we're now operating in meaning space. We don't just have like an index of the vocabulary, but we have a representation and attributions to the specific dimensions, they mean something. And from now on, we will only be using embeddings or representations when working with the neural networks in the settings of the talk. So, in my opinion, this was the kickstart for the language models as we know them today. In the coming years, they were developing these ideas further and eventually ending up at GPT-2. So we saw this mechanism, especially the one finding a representation for a whole phrase. And now I want to introduce you to the attention mechanism, which is the mechanism that is now used in recent models, which also serves the same purpose of like finding a representation of a whole text, right? That reflects the whole sequence. So when you ask yourself, okay, what do we need for this, right? We have a sequence, and we want to calculate one single representation of the whole sequence. So we might come up with questions like which word attends to which other word. We need to find that out. And then if we have to quantify it, we need to determine like in what sense does it influence the other word. And then we have to keep in mind that we might have different contextual aspects. For example, again, something that I just came up with, ideas to make it more tangible. You have a syntactic structure like subject, verb, adjective, noun, or semantic roles. So different scenarios where different words influence each other differently. And you have to take this into account. So I want to start with the idea of like, how do we find out whether or not like one word, you say, attends to another. So if this is relevant for this, right? And you start with car, and again, this embedding idea is everywhere, I have to say, right? So we have one more transformation into a subspace, and I call this query embedding. It's for the query part. You have two roles actually. One part is the query part. So the car is like, okay, who wants to attend to me? I'm a noun, say, right? Who is the adjective in the sentence? And then we have like a key or a response embedding that you apply on all the other words. And you find a representation in this subspace, in this particular subspace of this attention space. And then you can compare them. And when they're similar, you have a high score. That means, in this case, fast and car, they would be related, right? So fast attends to car in an example. I missed to mention the example sequence that I'm working with. The red fast car turned the corner, right? So this is the example sentence. And then you do that for all the words, but you only consider the ones which are in the past from the perspective of that word. So car shouts out, I'm a noun, who is an adjective, and then you find red and fast, and these attend to car, right? And the same for all other words. So this is the so-called attention pattern that you end up with. And so we have clarified the first question, how to find out what word attends to which other word. And now the question is, like, how does it influence the word, right? And so this is yet another transformation, but in the same dimension. So one, this is again the embedding word for red, and then we have what I call the change value transformation, whatever. But it takes this value and with respect to this particular aspect, like adjective, noun, for example, calculates the change that is then later on applied to car, for example. And so this is what we do. We now take a car in this example and then take this value that we have calculated here for fast, for example, and add that weighted by the attention score. So the more it attends, the more influential it is, and then sum it all up and end with a sum, like the total number of change, right? And the idea behind this is what you see here on the right hand side, right? So first, we might start with the representation of car, which is some generic car, and then you add red and fast to it. And you end up with a representation that represents something like this, right? And of course, you do this for all the words in one aspect-specific attention space. So this was number 2. We determined how the word influences it. Now number 3 is we want to consider different aspects, right? Like I said, aspect, adjective, noun, or we have word, noun, causality, and so on. So we give the network enough freedom to consider this and have just multiple so-called attention heads. And each attention head has its own parameter, its own transformation for query, key embedding, and change value transformation, right? So this is the building block of the multi-head attention, which is the mechanism behind transforming words and adding information from other words in the sentence. Okay. So the whole attention block consists of the attention heads that I've just discussed. Let's go one step back. Right here are the words forming the whole sentence, and we start with the embedding vector, with the original embedding vector that we found for each word, and then we pass this through all the attention heads that I've just described: query, key, value, edit, and end up with a new representation that is supposed to represent what this word means in the context of the other words that describe it, right? And then in one attention block, you have another aspect. You push these results through yet another neural network, right? And why do you do this? Because you want to associate stuff with words, right? Because this is, so to say, the internal memory of the network. So, we have the red fast car, that's kind of like Ferrari, maybe. And in this step, from the memory of the neural network that it has learned during the training phase, it adds contextual information or associations, right? It's like what people also do. Like, we hear car, we think of generic car. We hear red fast car, we think of Ferrari. And we add stuff like, associations like Maranello, sports car, Mustang, something like this. And this happens in this step. So in this whole attention block, you update each embedding by its preceding words, and then associate more information that is worth associating after transforming it. And you end up with another representation that's supposed to represent the word plus the associations, right? So that's the attention block.
Excuse me, what were
Yes.
it was the query embedding, and the second one, what was that again, like a few slides back?
I didn't go into details here. The query embedding.
So I could update it.
What's that?
Like you said, there were 3 different.
Yeah.
Like it was the query embedding, and there was a transformation thing, and it was
Key. The third one is the key embedding, or the key matrix. So you have the query matrix, the key matrix, and the value matrix.
okay.
Okay?
Thank you.
And I'm using slightly different terms here to make it a bit more, easier to understand.
May I ask a question?
Sure.
Because this reminds me a lot about. By the way, I don't know a lot about any of this, but I try to connect it with what I know. In politics, we will sit for hours discussing what one word we're going to use in a statement because of what impact it would leave, and it feels sort of similar to this. And I also reminded of a study in Norway where it was on Tinder. Like the word consultant was often associated with people that had like steady paying job and that were kind of smart, established. So what happened was that a lot of guys started, referring to themselves as consultants. If they did some sort of related work to consultancy, they were consultants. But what then happened was that the people that were actually consultants started looking for other ways to refer to themselves because the associations with consultant in girls went from steady paying job and intelligent to be liar or pretentious. So So they couldn't no longer call themselves consultants because associations with that word
Okay.
defeated the purpose. So they would have to hide the fact that they were consultants
Okay.
because it made a bad impression.
That's very interesting. Okay. So maybe this gets reflected if we put in like Norway alongside consultant and then
But
get some crappy words.
But this is like, do you think that it sort of fits with how this works, or how?
Absolutely. I mean, if you have this reflected in your cultural environment and you train a model with texts from that environment, this is reflected in the model.
So
And
it changes with time, but when associations change with the word, which happens,
Yeah.
Then it also changes to adapt to those new ones. Like
Of course.
our large language model, like ChatGPT, notices the change in the word consultant and its meaning in society context.
Most likely. I mean, it only does what you have told it to do. So it only reflects the training data, right?
Okay.
But that's a key thing, of course. It's very important what the data is you train your network with, right?
Okay, thank you.
Okay. Yeah, so this was quite challenging chapter. The key takeaways, right? This attention mechanism transforms the initial word embeddings to represent the entire preceding context in updated embedding vectors, right? So I'm not going through all of this, but we calculate the attention, calculate how it changes, and then we go through each word, and then do it for all the attention heads to consider all aspects. And when we have done this, we feed it through a neural networks to add it with associations to the state. And yeah, I would say we have found solutions to all primary requirements to find the sequence representations, right? And here, yeah, I have to say this deserves several medals. There are several good ideas in here, right? But let me say, it's really just about providing the structure that can reflect this. I said some things, some like tangible things in order to make the understanding better. But this is not going in there. Like there's no outside rules or something. It's just the flexibility of the neural network, and then it itself learns from the training data. Okay. So now we're getting to the really interesting parts. We've seen the attention block, and in the transformer, which is the model that we're using these days, in most current applications, just consists of a chain of these attention blocks, right? So what happens is, you start with a long text. You can put in really long text these days, and in the first step, you would only associate maybe what's in the neighboring context, what's mentioned, and so on, and come up with concepts in paragraphs and so on. And in the next step, you would consider these concepts, and so on and so forth. And through these iterations, you really consider each aspect of each part of the text. And now, when you take the last word in the sequence and then go to the last representation, then this last representation of the last word is like what I call the ultimate representation, right, of the text. So just in one single vector column of numbers, in this embedding space, all the information of the whole text is supposed to be encoded. And that's quite stunning, I would say. Right? So you have one single entity that represents all other text, everything. And from this, if we have like the ultimate representation, all we have to do is one more step, one more neural network from the embedding space, because we still have a representation, like an embedding vector, to predict the next word, the next token, right? And then you have the whole list of words and have your probability distribution. And that's the GPT without the technicalities. So the model that is like the foundation for all language models that we use today. So I was playing around with one of the earlier models, like GPT-2, and I put in a sentence, Cristiano Ronaldo plays the sport of, and I got this pattern as a result. So probability for next words. So what do you guess? What's the most likely word? What's the first word? Is it football or is it soccer? It's football. Thank God. So most of the text, most of the internet talks about football when it's about the sport that you play with your foot and not soccer. So that's good.
So
Sure.
this calculation is made for every single word that, for example, ChatGPT will reply. Let's make an example. How will be the weather tomorrow? So every single word that you will reply to me, it will pass all these steps.
Exactly.
And
I put it on the slide. Okay? How is text generated? You start with a sequence, what we saw. You pass it through this whole structure that I've described, the GPT, and you get a single token out. Just one word. A token actually, but let's stick with word. And then you just add the token to the initial sequence, have a new sequence, and put that back in. And then you get your next word. And this is the circle to generate the text.
So it's
Pretty crazy.
better to give like bigger sentences or or smaller sentences, because the bigger they are, the heavier the heavier the words. Even maybe the most important word will be heavier. Is that a good thing or a bad thing?
It's hard to say. I mean, today the models are so big, and we're speaking of so-called context length, when it's about how many words you can put in as the initial sequence, and they're huge, right? So you can actually put in whole books.
I'll make the same question in a different way.
Yeah.
If we make the same question to ChatGPT, but using different ways of making that same question, would it or could it reply us with the same answer or answer very similar?
If you ask it the same question,
It's the same question in different ways.
it depends. And there's
Temperature to zero.
there's some randomness, you can turn that off, but then of course the question is how similar are your questions, right? And that is also very subjective, and it depends on whether or not the network agrees to what you think is similar, right? So it depends. But now you know how the structure is and you can try it, and now you know what's going on inside.
But you will never get the same answer irrespective. If you ask the same question twice, identically, you will not get the exact same answer.
You get the same answer.
You get,
LLMs are
yeah, there is some randomness, but in the end, it depends on your seed value, and you can fix the temperature. It's beyond this talk, but it's a deterministic thing, right?
It's deterministic, so.
It's deterministic if you want it to be, and then you get the same.
That's because you set temperature, you set other system of counts that are deterministic.
Yeah. Okay, so we have the text generation. It's this. Yeah, so going back to our example, so what you put in this, and the first word is football, and then you put in this, you get 4, and so on and so forth. And here you see that ChatGPT, or GPT-2 is a bit outdated. Still thinks Ronaldo is playing for Madrid. Okay. But also recent models, actually. I generated this picture with Grok 3, thinks that Ronaldo is still playing for Madrid. Not true. Okay, so let's summarize this section. What we learned is the so-called autoregressive transformer, which is reflecting what you mentioned, that you only always get a single token, then you feed in everything and get the next token, right? So it's an iterative process, and that's a grand idea. I will not go into detail why, but it's a good idea. it certainly deserves a medal. Okay, one word to training and scaling up, because I will not go into detail, I didn't mention it, but you can imagine that it's kind of straightforward, right? You can just train on huge text corpuses because your input is just text, and the output that you want to have is just the next token. So it's very simple to generate like a large amount of data to train this, to have this kind of behavior that we want. I will also mention that, you know, when we think about AI models, we think of big compute clusters, but you essentially need the big clusters for training the models. The models are not that big that they need a whole cluster. They fit on a single unit, right? So it's not like that the AI is this gigantic brain. It fits onto one single unit, but for training, yes, that's very CPU intense, and you want to parallelize this and train on many machines in parallel. So let's come to some applications now. What can we do with this autoregressive transformer, right? The first application here is, can we turn this into a chatbot, the thing that we know? And of course, we just give it some instructions, saying you're a friendly, empathetic conversational AI assistant, and so on and so forth. And then here you put in your question, and then you say something like assistant, and then, it's supposed to generate an answer, right? This is essentially how a chatbot works. It's just by completing the sentence. And I tried this with, what's the question? Tell me, it's quite boring. And this is the output, right, of the tokens, token by token. Cristiano is a very talented footballer. Thank you. Another example, and I'm not sure you can read this from the back. It's quite an involved example, but it shows different aspects of, prompt engineering, and I want to quickly discuss this in the context of what we've learned so far. So it says you're smart, you're a math expert, you can solve like puzzles through careful step-by-step reasoning, and then you have a task of list that it's supposed to go through. And this is quite a sophisticated math puzzle. Okay, and 3 things I want to point out. So this is what we usually do in prompts. We set the perspective, right, in the beginning, because then by the whole transformer process and so on, it already is in a region in the space of representations where all the math puzzles live, so to say. We encourage it to go step by step, and we have very specific instructions. So now you all tried this, try to get an answer, and usually we see the entire answer, but we have to keep in mind that the answer is generated word by word, right? So it really starts from this prompt with this, for example, right? To solve this problem, let's break it down into manageable steps. So at some point, the input would be the prompt plus just the first sentence. And the first sentence, for example, you have because we told it to do this, right? This was the first instruction, break down the problem into clear manageable steps. So it goes and does it. And it starts with this. And then you take it from there. So now I have done it. So I start with step 1 and so on and so forth. Okay, so now you understand why this happens, because we set it into that perspective, and it's actually generating text word by word. So, each point in the answer, was once, so to say, the text that was going in. And then the rest was generated. And by the way, it solved this. This is a Llama 3 model. Quite nicely, right? But again, it's not a super intelligent solutions, because this is a textbook problem. You probably found it somewhere else, and the way to derive it. So one of the final applications that I want to show is tool use, and this is already for people who are actively using LLMs. It's an interesting aspect of LLMs. They have been fine-tuned to use functions. But when I say to use functions, they cannot call functions, right? LLMs cannot do that. LLMs are purely like text in, text out. They cannot call an API. They cannot run Python code or something. They can just indicate that they want to do that. And this is what most of the companies train them to do. And it works like this. You have like a system prompt which says your helpful assistant with tool calling capabilities, right? And then here it says respond in the format, name of the function, parameters. And you define the function as text, right? The name of the function, for example, get current conditions, weather conditions, and the parameters. And then you ask it, what is the weather like in San Francisco today, right? And this is the whole prompt, and the LLM knows, okay, now I'm supposed to tell the user that I would like to call a function. And the answer could look like this, right? Just text. But it says, I want to call the function get current conditions with these parameters, location San Francisco, and so on. And then you can call this function. Why am I telling you this? Because sometimes it seems hard to connect these language models with our normalized computer infrastructure, what we like and used for so long. And this is the solution to this, right? So you can call functions. And in particular, you can use it with, for example, a library called instructor that uses Pythonic. And the purpose here is to make use of this tool use aspect of the language model to assure normalized output. And so you define the structure as a Pythonic model. And this is not only a structure, but can also be called like a function, right? You call the constructor with the parameters. So smart idea would be to just define this as a function and say, okay, put this out, and if you want to call this, then go ahead and do. And this library actually does that for you. So you can just say, okay, the response model has to be like this, right? A text that has some information on the book, and then you're asking it to extract the book details from the given text. And then the library actually transforms this into a prompt which incorporates the call to the function, which is actually just the structure, right? But it adds this, and the model is smart enough in the response to indicate that it wants to call the function with the parameters, title, author, nationality, and so on. And you really end up with structured data. Now you get back like a book info type that you have title with, an author name, nationality. So that's very useful. Yeah, this brings me to my conclusion slide. So in this big award of key ideas of the transformer, the fundamental model for current AI applications, what we've learned is to start the perceptron, and we stacked it up and chained it together to have a multi-layer perceptron, plus the way of determining the weights of backpropagation. That's a good idea. Then we learned about representations, especially for words, right? Word-to-vec. That was, like I said, the ignition, in my opinion, of the whole process of having these AI systems that we have today. And to improve on that, we introduced the attention mechanism to have a better way of getting a representation of a whole phrase or sentence. We put this together into the transformer, so the combination of attention and the neural network to add some contextual or associative information to it. And we're using this transformer to predict a next word, a next token from a text. So the GPT, grand idea as well. And then I showed quickly how to bring back information from models into our normalized form. Okay. So the question is, although I was talking about text and chatbots and so on, I was starting with Google's autonomous car, and as far as we know, Tesla and its current self-driving cars is also using these same techniques of transformers to predict future outcomes in traffic situations. And eventually, it looks quite good. We will finally have a success, only because they gave up the idea of formulating like handwritten rules to drive a car in traffic, and just rely on AI models that they train on massive amounts of data, right? So this seems to be working. So final word. I would like to encourage you to see AI models as what they are. Don't be afraid of it. It's actually not that complicated, right? And see it as what they are, as tools that we can leverage to buy back time, to do what we actually like to do. And don't be afraid of AI. So spread the word, embrace AI, use it as tool, and then buy back time to do things you like and love. Okay? Thanks for joining. Okay.